from Cornell. Take it up.
Thanks to the organizers and thanks to everyone watching here and everyone else on YouTube watching it live. I'll be talking about statistical inference under information constraints. We'll focus more on the user level approaches toward the end of the talk. This joint work with Clément, Yuhan, Ziteng, and Himanshu. I put their pictures before the talk, so I don't spend too much time on this slide now. So we'll talk about, let's start with a very basic problem of Bernoulli estimation. You have NIID draws from a coin with bias P, and your goal is to estimate P. Okay, great. You just sum the xi's, divide by n, and show that the mean squared error of estimation is P times 1 minus P over n. Wonderful. Let's look at the same problem with a slight twist. Let's look at a distributed Bernoulli estimation where these n coin tosses are distributed across n users, and each of them can send 1-bit message to some referee R. Now you'll say, okay, you see 1 bit at each user and you have to send a 1-bit message. Each yi can just be xi. Nothing to do. So you can do whatever you're doing in the previous slide. Okay, so let's make it a little more interesting. What if these n samples are distributed across square root n users and each user has square root n IID samples, but they're still restricted to sending 1-bit messages? Pictorially, this is what happens. These yi's are still 1-bit, and this referee wants to estimate the underlying distribution. How well can they do it? So this is sort of the motivation for the talk. Now you can either think about it or wait for me to answer it later in the talk. This was like the opening. So here's the outline of the talk. We'll motivate the problem, give some precise formulations, talk about some of the oldish results that we have been working on for the past 3-4 years, primarily during COVID. So I've not given many talks on them. So I'll try to summarize some of those results and then move to some of the new results we have. Okay. Statistical inference. You have a collection of distributions over some domain X, and you get NIID samples from some distribution P that belongs to this class calligraphic P, and you want to solve some inference task. Okay, that's the highest level thing. In this talk, we will primarily look at discrete distributions. We have some results on other things, but 35 minutes is just not enough, 350 maybe. So let P be the collection of all discrete distributions over a domain of size K, and we will be primarily working with total variation distance. So just think of L1 distance. We'll look at 2 questions of interest. First is estimation, aka learning. Your goal is to output a P hat that such that the expected distance from the true distribution P is at most epsilon. And a complementary task is of hypothesis testing. In this case, we'll just look at what we call as uniformity testing, where U denotes the uniform distribution over K elements. And your goal is to design a tester T such that if P is equal to U, if P is the uniform distribution, you output 0 with probability at least 0.9. If the distance of P from uniform is at least epsilon in the total variation distance, then you want to output a 1 with probability 0.9. So this is learning and testing. But I have phrased this that, okay, you get to see Xn, the true samples, and then you want to do these tests. What we want to look at is the case when you do not get to see the exact samples. Okay, so you have only a limited amount of information about these Xis or Xts. For example, you may have communication constraints. Each of the sample maybe you have to describe them using at most L bits. Or maybe privacy constraints where you cannot disclose the underlying samples and they have to be somehow privatized. Maybe these Xis belong to some high dimensional space and you want to project them into a low dimensional space, and that's what you get to observe. Okay. So how can we model these local information constraints on the channels? On the samples? So the framework will be that there are n users. User T gets to observe Xt, one IID sample from the underlying distribution P, and they get to send a message Yt. We can model this as a channel Wt, where the input is the sample at a user, the output is the message that you get to see. Once the channel is fixed, because the input distribution is P of X, the output distribution is just given by Px times the transition probabilities of the channel. So the way we will model these local information constraints is by specifying a set of allowed channels calligraphic W, and each user is bound to pick one channel or their messaging scheme from this set of allowed schemes. This is how the picture will look like. You have a distribution, NIID samples, each sample passes through a channel, you get to see the outputs of the channel, and then your goal is to solve the same inference task as you did before. And maybe now you will require more data because of data processing. Okay. What kind of constraints one can think about? The easiest will be communication constraints. When the set script W is constrained to channels whose output is at most L bits long, or let's say L bits. So each XT has to be mapped to an L bit string. Or local differential privacy, starting with works of Warner, and there have been many new works on local privacy. Although in this workshop, I did not see that many works, presentations on local privacy, except maybe I first stopped today. And I'm going to call it as rho LDP. Okay. We have used epsilon. Okay. And the good thing is, although we'll present some results on privacy, I think the communication one is easier to communicate, and privacy is harder to describe clearly, right? Okay, so we will consider a set channel W is called rho LDP if the ratio of if for any input X and X prime and any output Y, the ratio of these transition probabilities is bounded by e to the rho. So you can get confused about the input. And we'll focus on the setting where rho is small, so e to the rho is 1 plus epsilon. Now, what is the question that we want to do? I claim that once you specify the channels, the job is done. Because once you specify the channels, the output distribution is just the product of each of the output distributions at the users, because the input distribution is IID. All the users have X1 up to Xn IID. Once you specify the messaging scheme, W1 through Wn, the output distributions of the messages are independent. So the entire question becomes, how do we optimally choose W1 through Wn? Namely, how does one decide the messaging schemes? Okay. Now here comes the interesting part. What kind of freedom do we have in choosing the channels? Okay. The easiest or the simplest case is when all the channels are chosen simultaneously, namely all the messages are sent out at the same time. So there is no interaction. Even here, something interesting can be asked. Okay, there is a distinction between private coin and public coin SMP. Let me just specify what it is. So in the private coin SMP, all the users just independently choose their messaging schemes. The easiest way to think is I fix the channels ahead of time. W1 through Wn are fixed. So in this case, all the messages are independent of each other. Slightly more involved setting would be what's called as public coin SMP, where there is a shared randomness that's available to all the users. And the users can now choose their channels, WTs, as a function of this shared randomness. So now the messages are not independent of each other. However, they are independent conditioned on the shared randomness. Okay. So pictorially, this is what it will look like. You have now a shared randomness across the users, and that's how the channels can be chosen. You can make it a little more complicated. You can say, okay, what if there is interaction? In this case, again, there is shared randomness, but now the messaging happens sequentially. Maybe I'll just go directly to the picture. So the first user chooses a W1, sends their message. Now the second user gets to see this message that the previous guy has sent. And then they choose their channel based on that, and so on. So each player chooses their channel as a function of the shared randomness and all the previous messages. Okay. So arguably, in terms of implementation, the private coin, no communication, no interaction is the easiest to implement. Public coin will be maybe a little more complicated, and interactive protocols will have like latency and other kinds of issues. And the question here would be, is it worth going into more complicated schemes statistically? Like, do you gain something by doing that? Okay, let's look at some of the results we have on discrete distributions, like the two questions that I asked before. Okay, for estimation under total variation distance, where your goal is to output a p hat that's epsilon close to the true p. The sample complexity or the number of samples you need to solve it is given by k over epsilon square, where k is the domain size and epsilon is the accuracy you want. Upper bound, just take the empirical distribution. Lower bound, apply Fano. Okay, so information theory almost 101. For testing, you can actually do something slightly better. You can do it with square root k over epsilon square samples. You need fewer samples. There are hundreds, okay, no, sorry, tens of papers proposing different kinds of schemes to do that. And the lower bound is basically Inkster's method that from like 80s. Most of these things just are beautiful variants of what Inkster said way back in 80s, I think. And so, for example, Paninsky gives one nice construction for how to apply it for this specific case. We'll just look at communication constraints for now. I'll talk a little bit about privacy, but it's later. So these messages are constrained to be L bits long. Now I'll say, okay, what if L is more than log k? Then there is nothing to do, because you have only a k, the domain size is k. If I have more than log k bits to communicate, I'll just send whatever I have. So that's why most of this part is at least interesting when L is small. And the first result that we talk about is this. So you had k over epsilon square, which was the sample complexity without communication constraints. Now there is this blow up of times k over 2 to the L. So that's the penalty that you have to pay. And once L is log k, this is 1. And this is true for all three communication protocols. You do not gain anything by shared randomness, not even by interactivity. So for example, when L is 1, you have a quadratic blow up. Like instead of k, now you need k square samples. For testing, actually, the scene is a little more interesting. For private coin simultaneous message passing, you get the same blow up, okay, k over 2 to the L. But if you have some shared randomness, you can do something much better. Now, instead of k over 2 to the L, the blow up is square root of k over 2 to the L. So in other words, with 1-bit communication, you pay linear in k instead of k to the 3 over 2 in terms of number of samples. So just the power of shared randomness for a very simple task of estimating of testing discrete distributions. So this testing work is from a paper from Colt, and then it is in transactions. So in one slide, I can write it all the results about communication constraints. So for estimation, private coin, public coin, interactive, no gap. Here there is a gap, but interactivity doesn't buy you anything beyond shared randomness for testing. Okay. And for estimation part, results were independently obtained by Han, Osgur, and Weisman. This part. Same thing can also be done for differential privacy. Qualitatively, all the results hold true. You gain something for testing under LDP with shared randomness. Nothing beyond that. All these three are identical. Okay. So that's all the results we have for local privacy. For testing, I think these results were obtained simultaneously by many people, including like Amin Mao Joseph and Beret and Butucia. And some of the results for estimation were proved. When I say some, I mean proving lower bounds for non-interactive schemes for estimation was proven in Ducci, Jordan, Wainwright. Okay. I think they claim not interactive results, but the proof doesn't go through. What's new today? I'll talk. So this was a recap of all the things that we did for many, many years. Yes, Peter.
Before we go to the new part, can you give us the intuition why public coin for testing helps and yes, it doesn't help for distribution?
Yes. Think of it like this. Let's say this is your uniform distribution, and your goal is to separate the uniform from an L1 ball. Let me just draw a circle. So when you don't have shared randomness, the people have fixed their schemes ahead of time. And now what the adversary can do is to choose, let's say you are, when you have shared randomness, what you can do is randomly pick a direction. And then with high probability, let's say this is the true underlying distribution. It's a min-max versus max-min question. Okay, who gets to go first? When you have shared randomness, you are going to choose the channel after I choose the distribution. In the other case, I get to choose the distribution and you get to fool me. So for example, if I choose the distribution here, what you will do is once let's say I select the channels, then you will choose a distribution that's going to fool my channel so that I'm not able to distinguish between the two distributions. On the other hand, if you get to go first, then I'll randomly pick some kind of channel that's going to, with high probability, give me some information about the true thing. And generally, this for most of these things, we actually have lower bound for general set of channels. So you take a set of channel, the calligraphic W, then we come up with a positive semi-definite matrix that somehow gives some characteristics of those matrices. And all these things that you see, there are various norms of those matrices that appear in this equation. So there is a trace norm here, there is a Frobenius norm here, there is the operator norm times the trace norm here. And all of those things, when specialized to these things, just give the tight bound somehow. So what happens when you have multiple samples per user? Okay, that's called user level constraint. So the talk will be based on these two recent works, one recent, one not so. So what is user level information constraint? You have instead of one sample. So previously we call it sample level results. Why sample level? Each sample was transferred into a message. Now it will be each user can have more than one sample, and that has to be converted into a message. So here, for example, each user has m samples, and the total communication budget is still L. Okay, so even if they get to see many more things, they can only send L bits per user. So now there is this tension of some sorts, right? You have more samples, so maybe you can do more processing, but you don't have maybe enough bits to send what you have processed. So that's the kind of question we want to understand here. So here W is a channel from m bit sample, from m samples to 0, 1 to the L. Exact same thing can also be stated for differential privacy, where now when you take the ratio, you can replace all the m samples of the user by something else. And this condition must be obeyed. Okay. We want to again look at discrete distribution estimation, but instead of sample complexity, because the results look very ugly. Okay, so we are going to consider, we will express some of the results in terms of rates. I'll come to this, so let's not worry about it until I come back. Let's go back to the beginning of the talk. The beginning of the talk, I said let's look at Bernoulli estimation. So that means underlying alphabet size is 2, and each user has only 1 bit to send. Right, so this is n users, each has MIID sample. So the observation at each user is just a binomial random variable, binomial MP. They get m samples from Bernoulli P, so they get to see binomial MP. And each user just sends a 1-bit message. And your goal is to estimate P. That was the first slide. If all these m times n samples are present at one location, you'll just do whatever we suggested in the very beginning, you'll get this mean square error. But now the question is, how can we, or what can we do in a distributed setting where, let's say, these n samples are distributed across square root n users, and each user can still send only 1 bit. And that's what we call as user level Bernoulli estimation with 1 bit. For example, the easiest attempts would be, I guess if you just decide to send one of your samples, that's not wise because you have so many samples, you'll just take a factor of m loss. So you don't want to do that. Maybe each user will tell you if there are more zeros or ones. Okay, let's start with that. The problem is if the true P is away from half, let's say it's a fourth or 3/4, then you will be seeing all zeros or all ones from most people just by concentration. However, if somehow this true P is close to a half, up to 1 or 2 standard deviation, that's why I wrote plus or minus 1 over root m. So each user has a binomial m comma P. So their standard deviation is about square root m, right? So if P belongs to half plus or minus square root M, then what can we do? Our goal is to get to 1 over square root of M times N. So can we just somehow transform from here? Actually, the answer is yes. What we will do is, if you already know that P is between half plus or minus 1 over root M, then each user is just going to threshold at half. If I see less than M over 2 samples, I'll send 0. If I see less than M over 2 zeros, I will send 0.
1.
I'll send 1. Otherwise, I will send 0. Okay. And what will you do? You have aggregated all of this. You'll just invert the binomial CDF at half. And that will be enough. It's just like, think of quantizing a Gaussian to estimate the mean. Even if you quantize to 1 bit and invert the CDFs, you'll get the tight bounds up to order factors. Okay. Something very similar here. Okay, so what does that mean? That means if we are able to estimate P up to the coarse factor, we are able to boost it up somehow. So a two-step approach would be first somehow come up with a coarse estimate for P, and then do a refinement by thresholding at your coarse estimate. So in other words, okay, if we do this, I think this is the result that we'll aim for. This first term is what you get when you have all the samples at one place. The second term is actually somehow necessary. Imagine the second term tells you that N shouldn't be too small. Why? Because imagine all the samples are at one user, but they have only 1 bit to send. Nothing to do, right? You need at least some users that will give you some more than 1 bit. Okay, so that's what this term captures, that N can't be 1 or 2. It has to be more than something. So now with interactivity, wait. The title of this should have been just interactivity. Okay. So with interactivity, now the scheme can be, it's pretty natural to implement, right? Okay, so we'll first come up with a coarse estimate by just doing a binary search. Okay, so you start with, let's say, thresholding at M over 2. You keep seeing a bunch of zeros. So you go to threshold at M over 4, maybe at 1/4. Keep doing it until you get a rough estimate of P. And then you just threshold that place. So the most interesting part of this work was actually to come up with a non-interactive estimate that's able to do these reasonably intuitive steps that we saw. How to implement all of those things without interaction. So that's what I'll just discuss a little bit now. Still, the coarse estimate part is not that complicated. We'll see. So what was our goal? Our goal was to estimate the P up to a standard deviation around its true value, right? So what we start off with is take 0 through M. That's the set of observations that a person can have. They can see from a single one, from 0 ones all the way up to M ones. That's what each user sees. They just get M samples, right? We partition this interval into roughly square root M intervals that are growing in size up to a half, because that's so the width of each of these interval is growing linearly, order I, and that's roughly the standard deviation. So if M times P is in a particular interval, the standard deviation will be roughly the width of the interval. That's what we want to do. So maybe we can first set aside some users that are going to send 1-bit information about which interval they are in. Okay. There are many ways to do it. I think the cleanest approach that at least I think is the cleanest approach is to just use a gray code to specify these intervals and just send bits for the gray code. And this was also used in Tsai and Wei for Gaussian estimation. If nothing, I think most of you know gray code. If not, maybe that's the one thing that you can learn from the talk. So what's a gray code? Gray code is a binary representation of numbers from 0 up. So what's the mistake here? 0 up to -1. Okay, with S bits. So the nice property here is if you look at 2 consecutive numbers, they differ in exactly 1 bit. So now if you assign this to the intervals, if you make a mistake in estimation, you're just going to end up in an interval that's adjacent to you. Okay, you won't end up across the country or something. So now that's the first step. So you have come up with a partition of the intervals. You first take a subset of the users that you are going to just use for this coarse estimate for the first step. You partition them into S groups. Each group is now just going to look at the interval that their sample falls in and send the jth bit of the gray code representation of that interval number, basically. And you'll just take a majority vote. And finally, whatever you end up with is your course interval. Okay, so that you do with half of the users. Now you have a course estimate. How do we do refinement without interaction? So now you have a course estimate. If you just have one more, if you can just send that information to everyone else, you're golden. You can just threshold there. So how do we do that without interaction? The course threshold could be anywhere in this entire range, right? What we will do is to just use multiple thresholds. So we'll come up with some kind of pulses. This is very close to the same interval scheme that we saw before. And if the number of ones that you have falls in the red things, you are going to send a 1, otherwise you'll send a 0. This actually almost works. There is one very nice sad thing that happens, which is if the true P falls in the middle of an interval. So what are we trying to do? Okay, we are somehow going to use the information that we have from the first half to get a course estimate of P. Then we want that when P, so now let's say we know which interval P is. What you want is when the P changes, you are able to detect it by thresholding. Okay, that's the whole thing, right? You are trying to invert a binomial CDF. When can you invert? When actually changing the parameter changes your distribution that you observe. Otherwise, you don't see anything. If I change the parameter and what I'm seeing has the same distribution, I don't see anything. I think I need just a couple more minutes. Okay, we have a lot of time. Suppose your P is in the middle of the interval.
7 minutes.
Okay, I'm on slide number 44. Oh, it's here.
I don't see the upper bound, so I have no idea.
It's less than 60.
I'll ask him to-
Yeah, 30 minutes, so roughly two per minute, right? Okay, but what if P is exactly in the middle of the interval? If P is exactly at the center of an interval, when you move P a little bit to the right, you're going to lose some mass on the left, you're going to gain some on the right. If you move it a little bit to the left, you're going to gain some on the left and lose some on the right. So essentially, when P changes around the center of an interval, you'll not be able to detect it quickly. It's almost like the first order of, you want to invert a function, right? So if you want to invert, you want it to have a behavior like this, so that if you change the parameter, you can detect it on this axis. But if you change the parameter and this is what you see, and this is the parameter. If it's flat, you can't invert it. That's it. Okay, and that's what happens if the true parameter is in the middle. Okay, so what do? You come up with another fix. What's the fix here? The fix is just take another set of intervals that are just these things shifted by half of the interval. Then what you can show is, regardless of the value of P, at least in one of these, changing the P changes the distribution of the thresholded CDF or the quantized outputs. At least in one of these cases, the derivative will be large. You take that, invert the binomial CDF, and you get your. So this is all the work that we had to do to get a 1-bit estimator for a Bernoulli random variable when there are multiple samples per user. Okay, so what do we do with it? Now we want to extend it to k-ary distribution. Now let's recall. To estimate a distribution up to total variation epsilon, you need k over epsilon square samples. Now, for some reason, I don't want to write results like this. So what I do is I want to write the results in terms of TV error. You'll see why. So the same thing, you equate this to n and then write epsilon in terms of k and n, you get this. Okay, that's the math. So for m equal to 1, this is the result that we started off with. The blow up in sample complexity, instead of just this n, now you have to deal with this k over 2 to the L factor that I said in the very beginning. What can we say when instead of m equal to 1, there are multiple samples per user? Okay, can we do something as if something nice? Okay, let's see. So first result is that when m is not too big, when m is less than k over 2 to the L, and n is reasonably large, and large we need for some reason. Then this is the optimal sample complexity up to constant orders. So in other words, having each user has m samples and sends L bits, it's the same as if you have m times n users and each user sends L bits again. So where are we gaining or losing, right? So the point is, if you have m times n users and each user sends just L bits, they have only one bit. So they can't really do anything smarter with all the samples that they have. So that's the takeaway here, that it's as if you have m times n users, but each can send an L bit message. So you need a lot more communication. Okay. And for the other regime, we have some results. I want to just say that they are tied up to log factors, but there is something nice that happens. This 2 to the L gain you get, actually it happens only when m is small. Once m becomes too big, you don't get much of a benefit. You don't get the exponential benefit that you would want. Okay. There are some intuitions for that. We can talk later. Let's give a sketch for, okay, how do we boost this algorithm? Like we did all the work for binomial. Maybe we can just finish by extending it to general K. I'll give a very simple sketch. The algorithms are not that complicated. I think all the work goes into lower bound, but lower bound, as I said, will need 350 minutes that I don't have. So what we do is you first partition K into K over 2 to the L blocks. Each block is of size 2 to the L. Why 2 to the L? Because if I know the block, I have enough bits to send which sample I'm seeing, or at least one sample within that block. Step 1 is we'll just consider these K over 2 to the L blocks and look at the distribution induced over the blocks by P. So now your alphabet size has reduced from K to K over 2 to the L. What we'll do is just take half of the users that you have and divide them into B groups, into the number of groups that's the block. So each person is responsible for one block. Each of these small groups is responsible for one block. So what they do is just run the 1-bit protocol to estimate their block probability. So take half of the users to estimate the probability over the blocks and divide those users into how many ever blocks you have. Each user just sees the samples, and for them, the only question is it in the block that I'm responsible for or not? And they use the 1-bit scheme. In the second case, you are going to compute conditional distribution. You do again very similar thing. You divide the rest of the users into groups. And what those users will do is just check their first sample. If it is in that block, they are going to send its binary representation. Otherwise, they'll just send maybe nothing. This is very interesting. The first half, the users are just going to use 1 bit out of the L. They are not going to use anything. In the second half, the users are just going to use 1 sample, even if they have m samples. And somehow doing these two things, which are in themselves suboptimal, turns out to be the optimal thing to do. So first half of the users will just send 1 bit, even if they have L bits. Second half of the users have m samples each, but they will look at only 1 sample. And you combine these two things and looking at all the results that we have proved until now, I think you should be able to derive this result. It's just given whatever we have proven until now, if we just go through. As I said, lower bounds are hard for these things. And I think half of our time out of those 3 years went in realizing that many of the lower bounds claimed in other papers didn't go through. So first we got some of these lower bounds, we were very happy. Then we said, oh, okay, let's see if we can rederive those things. And why are they getting stronger bounds than us? I mean, and turns out that you can look at this paper. We complain a lot about many of the other works if you like having fun with such things. Thank you.
1 minute for a question while we set up Adam, who's online. Yeah.
Yes, Lenny.
Is the final estimator unbiased or biased?
Is the final, what does that mean here?
I mean, you have a like for the Bernoulli test, you have an estimate for P, right?
Yes.
Is this estimator biased or unbiased?
Is this estimator biased or unbiased? I think it's definitely biased the way we are doing, especially with inverting the binomial CDF.
I have a comment. And it goes back to that last slide where you said some lower bounds don't go through. We observe similar things in our GANs context, but I want to ask you a broader question. Can you ever do any other F divergence space? Non-semi-metric distances to get any lower bounds.
So once I think that if the distances have some other triangle inequality or something like that, I think many of these lower bounds will go through, not just with L1 distance.
Right.
I forgot to mention. So for local privacy, all the results go through. Okay, we spent a lot of time on communication, but privacy also you can get results with similar techniques and maybe a little more of the messy work that we have to do.
Do you have any sense of how like the bounds would scale with dimension? So if instead each user had, D or M samples of like dimension D.
Yes.
Because now the blocks.
So in those cases, yes. So there is a lot of work. So the easiest question to ask is, okay, let's say you have a d-dimensional Gaussian. D-dimensional Gaussian standard covariance, you want to estimate the mean up to L1 distance, L2 distance epsilon. But now let's say they are distributed across users. Each user gets to send 1 bit. So then naturally, if the dimension goes from D to 1, you will get a blow up of D. Instead of D over epsilon square, which you will get if all the samples are at the same place, you add them up, divide by n, you get D over epsilon square. That will become D square over epsilon square. However, the lower bound for interactive, even for that simple question, I believe is open. It was claimed in a work of like Braverman, Gerb, and Woodruff. But I think the lower bound breaks there also. So even for this basic question, we do not know what the answer is. Just Gaussian distribution distributed 1 bit per user. I think it's open. So under interactivity.
Our next speaker is online. Doesn't need much of an introduction.